Okay, so for the chapter of stereoisomerism, we will be covering compounds that not just have the same molecular formula, but they indeed have the same structural formula. All right. However, the only thing that they differ is in the arrangement of their atoms in three-dimensional space. Okay. Now, there are two types of stereoisomers. Number one is called a configurational, which is what we are going to cover today's lesson. Conformational is no longer in your syllabus, but it can appear in paper 1B as a database question. Now, there are two types of configurational isomerism. We call it cis-trans or EZAC and optical isomerism. So I'm going to toggle guys between this as well as your chem guide so that you guys are very well aware of what is tested and what is not tested. Okay? Okay, so if you take a look at the screen guys, you as an IB student need to be able to describe and explain the features that give rise to this type of isomerism, albeit non-cyclic alkenes, as well as carbon 3 and carbon 4 cycloalkanes. Okay? Can? So, if you take a look at cis-trans isomerism, guys, cis-trans isomerism arises due to what we call as restricted rotation. Now, what exactly is restricted rotation? Restricted rotation arises. I want you all to take a look at this ethene molecule. I want you to focus on the pi bond. Now, pi bond arises due to sideway overlap of parallel p orbitals. Are you all able to see the purple color p orbitals? They do a sideway overlap for you to form a pi bond. Do you all agree now? Mm-hmm. So any form of rotation of one carbon atom would result in the breakage of the pi bond. Does that make sense? Mm-hmm. So in translation, guys, okay, in translation, if I were to, okay, ignore the name cis and trans, I'm just going to say molecule on the left and molecule on the right. If I were to hold the carbon atom on the right while twisting the carbon atom on the left so that the X will go downwards while the Y will go upwards, that will cause the pi bond to break. Correct or not? The pi bond to break. And therefore, after the pi bond breaks, you rotate and reform the pi bond again. Now, breaking, reforming is a chemical process. It is not a alright? It is not a, what do you call it? It is not an actual, what they call it? It's not an actual physical process. Physical process means you rotate. Are you all clear now? Physical process means rotation without breaking any form of covalent bonds. Are you all clear? Can understand, guys? Yeah. Are there any questions here before I carry on why cis-trans isomerism results in this? No? Yes? Okay. Okay, hang on. I did text him. He's replying. Okay.
Where was Bonnie last night? I saw you. No, say no, very far away. You never called me. No, I don't know. I was phoning you. What are you doing? Too low. What's
that? What's the E?
Hui Min.
Okay, we are currently on page number 25. All right. Okay, just for the benefit of Oliver, right? So Ollie, we are actually looking at molecules that have the same molecular formula, the same structural formula, right? But their orientation of their atoms in three-dimensional space is different. So these two molecules are mutually exclusive. All right? Why? Why are they mutually exclusive, guys? Because there's a pi bond here. Look here. There's a pi bond here. Any form of rotation would result in the breakage of the pi bond. And then you rotate it. You rotate the carbon on the left. And then reforming the pi bond again. So breaking, rotating, and reforming constitutes a chemical process and not a physical process. In translation, these two molecules are mutually exclusive. Are you all clear? So the molecule on the left is different from the molecule on the right. They cannot interchange just because we keep on rotating. Clear on this?
Why does it rotate?
Sorry?
Why does it rotate?
It rotates wait. All right.
Since it's the same molecule.
No. Okay, so the question, wait, I answer Kian's question first. Kian asked, why, the first question is, why did it rotate? Correct? It's not that it rotated. People, when take a look at these two molecules, right, they thought that they are actually the same molecule. It's just that one is just a rotated form of the other. You all understand, no, guys? But actually, these two molecules are completely different. Now, you might be thinking, why do people think that? Why do people in the past actually think that these two molecules are the same? That's because sigma bonds are constantly rotating. You will learn in the next chapter, yeah, when you deal with infrared spectroscopy. When you pass IR radiation to molecules, the sigma bonds will start rotating. And because we are surrounded by visible light, as we are speaking, the sigma bonds in a particular molecule, let's say oxygen, let's say nitrogen, they are rotating, guys. So, I mean, inadvertently, when people see these two molecules, because they have the notion that sigma bonds are constantly rotating, they would think that these two molecules are identical. But actually, these two molecules are different. So, what I have done today is I have grouped them as molecule on the left as well as molecule on the right. You all understand, guys? Okay, so if you take a look at these two molecules, it is very, very important for us to learn how to name them. And this is where it gets a bit more dicey. Now, if you all take a look up here, there's two types of naming for cis-trans isomerism. Cis-trans isomerism or EZ isomerism. You can see that? Okay. Now, you might be thinking, what's the difference between the two? Okay, so let's start off with cis-trans. Cis-trans is like the rigid version of EZ isomerism. If you want to put it into context, it's like cis-trans is Arrhenius' definition, EZ is Bronsted, where Arrhenius is a lot more rigid in terms of his definition as compared to your Bronsted. Are you all clear? So let's start off with the requirements for you to be called a cis-trans isomer. Number one, each doubly bonded carbon atom. What do I mean by each doubly bonded carbon atom? The carbon on the left as well as the carbon on the right is called doubly bonded. Each doubly bonded carbon atom, we start off with carbon on the left, must have two differing substituents. Are you able to see X and Y as two differing substituents? Yes. Now the carbon on the right must also have two differing substituents. Do you see carbon on the right have two differing substituents? Yes. So it meets the first criteria. Now, the second criteria will be, what's the second criteria, guys? The second criteria will be across the doubly bonded carbon atom, there must be similar groups. Alright, across the doubly bonded carbon atom, there must be similar groups. So I want you all to take a look at this molecule again. Are you able to see that the similar groups are X across the doubly bonded carbon atom, and the X or even the Y are on the same side? And in Latin, same side means cis. Alright, let's take a look at the molecule on the right hand side, guys. Let's go through the criteria again. Each doubly bonded carbon atom must have the same groups. So must have different groups. Do they have differing groups or not? Each doubly bonded carbon atom, they have differing groups, right? Very good. So criteria number 1. Criteria number 2. Across the carbon-carbon double bond, there must be similar groups. Have is X and Y, right? And X and Y are diagonally across. In Latin, diagonally across means trans. Understood, guys? Hence the term cis-trans isomerism. Now let's give it another try. I know that this molecule is not provided to you. I created them for the 3 classes that has passed by. Okay, so are you guys also able to see this molecule? Let's start off with criteria number 1. Each doubly bonded carbon atom has different substituents. Across the carbon-carbon double bond, there is similar group. So therefore, for the first molecule, the similar groups are cis, right? The first molecule is trans because they are on opposite side. Yes, and then this one here will be cis. Are you all clear? Okay, you can understand now, guys.
Yeah.
Now, just in case you are not very sure what is criteria number 1, all right. Criteria number 1, if you notice over here, has a carbon atom with 2 hydrogen atoms. So means each doubly bonded carbon has substituents that are the same. Okay, clear? Any questions here, guys? Okay. Now, I want you all to take a look at cis-butene and trans-butene and see whether or not you all are able to agree with this. Okay, are you able to agree? I do not know this one. Turn to the next page.
Maybe rockets. It's a man rocket.
Can May I? Do you all understand cis-trans isomerism now? Later we will study the physical properties of cis-trans isomerism, okay? Now, the molecules that you all said look like rocket. Okay, let's go back to your chem guide, guys. We have covered the first part. Let's recap. Describe and explain. Okay. The features that give rise to cis-trans isomerism. Come, guys. What's the word? Why do we call it describe? The features. So if you want to describe the features, is restricted rotation about the carbon-carbon double bond. That's called describing. Now let's explain the features. Explain. Any rotation would lead to the breakage of the pi bond. Am I right, guys? Yes, so that is explain the features that give rise to cis-trans isomerism, recognizing it as non-cyclic alkenes. So we have done non-cyclic alkenes. What's the next thing that we have to do? Carbon 3 and carbon 4 cycloalkanes, the molecules that you're looking at right now. So we are now dealing with this part of the syllabus, yeah? Carbon 3 and carbon 4 cycloalkanes. Is that clear? Okay, so I would like you guys to take a look at the very first example. You have cis-1,2-dimethyl cyclopropane. Can you see that? Okay. Before we start, let's figure out. Let's go back to the question is describe and explain the features of cis-trans isomerism. Okay, let's start off with the very first one. Are you able to see that this particular molecule here, all right, has a triangle structure? Okay, now the angle in a triangle, guys, provided they are equilateral, of course, is 60 degrees. Am I right, guys? Now, if you notice, each carbon atom here is sp3 hybridized. And the recommended bond angle for you to be sp3 hybridized is 109.5 degrees. Correct or not? sp3, the recommended, what's the recommended by who? Recommended by VESPA. This 109.5 ensures that you have minimal repulsion by having maximum attraction between bonding electrons. That's the principles of VESPA. You all agree now, guys? Now, people recommend you 109.5, but you go and build a molecule that is 60 degrees. What's going to happen? What do you think is going to happen? People recommend you 109.5, but you decided to build something that is 60 degrees. You're going to have a lot of strain. Very good, a lot of repulsion. The repulsion results in strain, correct? We call this angle strain. Understand, guys? This means that any slight movement or rotation of the structure will cause the structure to break apart, to crumble. You all understand? No? Yes? You all agree, guys? So, what we're going to do today is, if you take a look, we're going to use the principles of cis-trans isomerism, which is the first criteria. What's the first criteria, guys? Each doubly bonded carbon atom must have two differing groups. Okay? But this one got no doubly bonded. So I want you all to take a look at each sp3 carbon atom must have two differing groups. So obviously this carbon atom is out, right? Because this particular carbon atom got two similar groups. So I want you all to focus on the carbon atoms that has two differing groups, shall we? So now, guys, are you guys able to see that? Let's go to the second criteria. What's the second criteria? Across the carbon-carbon bonds, there must be similar groups. So are you able to see that the two CH3 groups are on the same side? And in Latin, same side means cis. Clear? Now, I want you all to go over to the molecule on the right-hand side. If I were to do any form of rotation, guys, of the CH3 group on the left-hand side and rotate it 180 degrees downwards, like this, 180 degrees downwards, that will cause the breakage of the pink color bond. You can see, no? The pink bond will be broken. Once bonds are broken and bonds needs to be reformed, that's not a physical process, yeah? That is a chemical process. And therefore, these two molecules that have been drawn for you are said to be mutually exclusive. Means they are two separate molecules, they have their own physical properties, they have their own density, they have their own melting points as well as boiling points. Completely different. That's why when they define stereoisomers are defined as same molecular. They have the same structure, as you can see, but their orientation of their substituents in 3D space is different. Are you able to see that they are orientated differently, guys?
So because they rotate, their properties are different.
Sorry again?
Because they rotate, their properties are different.
No, not because they rotate, their properties are different. It's because of the positioning of the substituents that their physical properties are different. I will explain the next page. How come their properties are different? Is that okay?
How different can it get?
Huh?
How different can the properties be?
Like for example, their melting point, the trans molecule could be higher than the cis molecule.
But is it like a big difference?
No, not a huge difference, but it's still different. You see, if you synthesize the wrong molecule, especially in medication, guys, it could cause either no effect at all on the person, means you don't even feel better after eating medication, that's one, or it might cause deformities. Alright, and this is an example that we will use in the next type of isomerism. Are y'all clear now, guys? So, being able, guys, to recognize that these two molecules are different, alright, being able to recognize that these two molecules are different is very, very important. Because in the grand scheme of things, if you synthesize the wrong molecule thinking that the molecule is exactly the same, it might lead to detrimental effects. Y'all understand not? What I'm trying to say here. Now, have you all heard of this word called trans fat versus cis fat? Have you said trans hyphen fat?
Yes.
Like fat around your arteries are called trans fat. The word trans comes from this. It is because when you have fatty acid molecules, they have carbon-carbon double bonds. And because of the restricted rotation about the carbon-carbon double bonds, it results in the formation of this. Are you all clear, guys? And trans fat, I do not know whether you all even know this as a form of general knowledge, is more unhealthy as compared to cis fat. Alright? Clear, guys? Now, to complete your learning, your syllabus covers carbon 3 and carbon 4. Am I right, guys? Now, the angle in a square is 90 degrees. Are you able to see that? But the recommended angle that is given for sp3 carbons are 109.5, correct? No? Do you all agree? It's 109.5, yes? So the angle, the deficiency of angle of 19.5 degrees, right, is primarily due to angle strain. Do you all agree not? Or would lead to angle strain. So cyclobutane would also experience the cis-trans isomerism, or we call as restricted rotation, about the carbon-carbon single bond. Are you all clear now, guys? Now, you might be thinking, then how come the syllabus stops at carbon 4? How come the syllabus doesn't go to carbon 5, carbon 6, carbon 7? Because if you study E-math, you would know that the internal angle of a polygon gets bigger and bigger as your ring gets bigger and bigger as well. Carbon 3 is 60, a triangle is 60, a square is 90, next will be a pentagon is 108 degrees, correct or not? As you get closer and closer to the target, which is 109.5, yes, if you get closer and closer to 109.5 means your angle strain will be lesser and lesser. So there will no longer be restricted rotation. And that's why you don't observe cis-trans isomerism in rings that are carbon 6 and above. That's why your syllabus only deals with carbon 3 and carbon 4. Understand not? Because only in carbon 3 and carbon 4, the internal angle, right, is very far away from the recommended 109.5. And that's why there's restricted rotation. Are you all clear not? Yeah. Okay? So let's recap, because this is a very important part of organic chemistry. How come cis-trans isomerism arises? It arises because of either restricted rotation about the carbon-carbon double bond. And why is there restricted rotation about the carbon-carbon double bond? Because, guys, when you form a pi bond, there is a sideway overlap between parallel p orbitals. Clear? Any form of rotation of these p orbitals would result in the breakage of the pi bond. And once you break the pi bond, rotate and reform the pi bond again, that is a chemical reaction. That's not a similar molecule any longer. Now, why is there cis-trans isomerism in carbon 3 and carbon 4 cycloalkanes? And that's because the restricted rotation arises due to angle strain. Understand, guys? And the angle strain arises because the recommended angle is 109.5, but because carbon 3 is 60, carbon 4 is 90, there's a lot of angle strain that is being placed on the sigma bonds. So any rotation will result in the breakage of it. Are you guys crystal clear on the first learning objective for today, which is describe and explain the features that give rise to cis-trans isomerism, recognizing it in non-cyclic alkenes and carbon 3, carbon 4 cycloalkenes.
Wait, it used to be carbon double bond, right?
Sorry
It
again?
used to be carbon double bond, right?
What is carbon double bond?
Like when this thing.
Yeah, that is carbon-carbon double bond.
Then here.
That one is not carbon-carbon double bond. That one is carbon-carbon single bond in a ring. Yes. So, two concepts. One line has two concepts. Non-cyclic alkenes is restricted rotation about carbon-carbon double bond. Carbon 3 and carbon 4 cycloalkanes is restricted rotation about the ring.
So only other be
Yeah. So for IB, it will only test you carbon 3 and carbon 4. But I teach you all carbon 5, carbon 6 so that you all complete your learning, that you all understand why carbon 5 and carbon 6 got no cis-trans isomerism. That's because the internal angle of a polygon gets bigger and bigger, right? As the number of as the carbon atoms increases. And when that happens, you get closer to the targeted 10 or the recommended angle of 109.5. So just in case you all are wondering why you only do carbon 3, carbon 4. Okay?
Or is it like if you like how to share?
What left?
Fuck. I forgot.
This speaker ask question for me.
Thank you.
Another few thoughts.
Like
Yes.
when you put like the repelling magnet together, then if it repel, then it just keeps switching around. Like going back and forth.
Yes, you got it.
Until
No, then
Which one?
repel this part of the screen.
But there's no repulsion here.
But
Hey,
Huh? Okay, I checked something, but I checked my package, okay? You went and freeze.
I give up.
This guy.
Don't really ask the question.
Do you even listen in class?
What?
Okay, do you listen in
To
your
what?
class? Yeah.
I'm not even there.
Bro was dead asleep.
He's been asking what?
Wait, what magnet are you going on?
Yeah, I have no clue. Shut up, bro.
You make up, bro.
Okay. Now, I just want to highlight that the nomenclature means naming using the EZ system will not be assessed. That when they say naming, all right, will not be assessed means they will not ask you to name molecules with the E and Z inside. But that doesn't mean that it stops them from testing you on which one is E and which one is Z. All right, so I'm going to go to the looser definition of cis-trans isomerism, which is on the next page, which is called EZ isomerism. Are you all following? All right, guys. I want you to take a look at this alkene molecule right at the top. Okay, so for this particular alkene molecule that you see right at the top, right? Let's start off with the very first, the very first criteria for you to exhibit the type of isomerism that I just taught you. Number one, you need to have, not just double bond, you need to have each carbon atom, doubly bonded carbon atom must have two differing substituents. You see X and Z, right? And then the next one is Y and W, right? So it meets the first criteria. But if you notice, the second criteria is not met, which is across the carbon-carbon double bond, there must be similar groups. Is there any similar groups? Don't have. So that's the difference between cis-trans and EZ. EZ isomerism only meets the first criteria, never meet criteria number 2. And you might be thinking, why do we still want to name them as a form of cis-trans isomerism? Because you must understand that the chances of molecules having similar groups across carbon-carbon double bond is very, very rare. So you are restricting, by putting the second criteria, you are restricting a lot of molecules. You'll understand? Then a lot of molecules got no names, got no categories that they belong in. So by removing the second criteria, there'll be a lot more molecules that can be included in this particular stereoisomers. You all understand? Are you all clear not? Why they moved away from cis-trans isomers and moved towards EZ? Because having two criteria is just too rigid. Just like think about Arrhenius' definition of acids and bases. You need to dissolve in water, that's one. And then you need to produce H plus or OH minus ions. That's literally ruling out almost a lot of things already. So that's why the Arrhenius definition is being more, they make it more loose and move it to Bronsted definition. And they realize that Bronsted still too rigid, they move it to, what's the last one? Lewis definition. Clear? So I do hope that you all are able to see that EZ isomerism, right, is a form of cis-trans isomer. Are you all clear on this? Can? All right. So let us take a look at let us take a look at this and how to name them. So we're going to label the carbon left as well as carbon right. So we're going to go one by one. But if you notice, I would like you guys to take a look at how we group them in terms of priority by these three scientists, Kahn, Ingold, Prelog. We look at the atomic number rather than the atomic mass. When someone says atomic number, that means proton number. Is that clear, guys? So, hello. So, guys, if you take a look at the carbon on the left, all right, if you take a look at carbon on the left, bromine has a proton number of 35. Am I right, guys? Hydrogen has a proton number of 1. So, could you advise me who is bigger, 35 or 1? 35. So, you circle the priority group. Okay, now we move on to carbon on the right, shall we? Carbon on the right, both carbon atoms has 6 protons. Okay? Both carbon on the right has 6 protons, right guys? Can see that? So it is a tiebreaker. So to break the tie, what do? You move on to the next carbon atom. Can see? So if just in case you all don't understand, you see for this carbon atom in purple, the next atom is hydrogen. What's hydrogen's proton number? 1. Very good. This carbon atom, what's the next atom that he is bonded to? For those who really cannot see, I draw out is in full structural formula. The next atom is also carbon. Carbon 6. This one, hydrogen, is 1. So between 6 and 1, who bigger? 6. And that's why this is the priority group that I circle in red. Now, since the two priority groups are on the same side, in German, same side means zusammen, which is then represented by the letter Z. Alright? That's why they put Z in front, to tell you that is the two priority groups are on the same side. So zusammen. Clear? The opposite of zusammen means opposite side. In German, we call it Entgegen. Entgegen means opposite side. So the letter E. Please, you do not need to know the German terms. I'm just telling you again, just to complete your learning. Alright?
Silent German is it? Right German is it? Is it silent? Is it?
Okay, may I carry on? Yes.
What if instead of CH3 it was CN?
Then, okay, so he asked what happens if one is CH3 and the other one is C triple bond N. Okay? A triple bond will always be ranked higher than a single bond. Understand? So if you go back up, just in case a single bond, when someone draws for you a triple bond like this, it translates to this, yeah? A triple bond translates to like that. Is that okay? So our CH3, right, is carbon, hydrogen, 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 right? So if you were to make a comparison, you realize that he will lose to nitrogen lah. So the C triple bond N will be chosen. Okay?
Number of protons.
Yes, because the number of protons, that's 1. The second reason is C triple bond N will be ranked above a single bond. Clear? Alright, let us move on to physical properties, guys. There is a typo. Can you all please edit the typo in your lecture notes? The molecule on the left is trans, the molecule on the right is cis. Then, typo. Are you able to find the typo? Trans? So just now, I think someone was asking me about physical properties. How does trans differ from cis in terms of it? I think it's Oliver, right? So we are now taking a look at this particular example here. Alright, as you can see here, this is the melting point. I know that it looks stupid for me to write down here solid to liquid. Now, there's a reason why I purposely put it solid to liquid, because the physical properties for melting point, for cis trans, differs from the boiling point. You all understand? No? And that's why I have to indicate it very, very carefully. Now, why did I put the word solid here? I put the word solid here to tell you, or to ask you all to imagine in kinetic particle theory how solid particles are arranged. Number 1, they vibrate about their fixed position, right?
Yes.
Number 2, they have damn low energy. They have the lowest energy among the 3 states. Agree? So they vibrate about a fixed position, they are fixed, and then they have the lowest energy. So right now, guys, because we are talking about how well you pack, right? How well your molecules are able to pack. So we are going to do a comparison between trans and cis. As you can see, these two molecules are hydrocarbons. Hydrocarbons means you are only made up of hydrogen and carbon. Agree? So therefore, your whole molecule is non-polar. Am I right, guys?
Yeah.
Yes, very good. So because both molecules are non-polar molecules are held together by London dispersion forces. And London dispersion forces are affected by two things. Size of electron cloud, number one. Number two is surface area of contact. Let's go through number one. Size of electron cloud. They are isomers. Obviously, their size of electron cloud is going to be the same because they have the same molecular, they have the same structure, so the size of electron cloud going to be the same. However, for isomers, their surface area of contact differs. Understand, guys, for these two. So let's start off with the cis isomer. Alright? Because the two bulky groups are on the same side, when we try to pack them very, very close together, what is going to happen will be there'll be a lot of repulsive forces between the groups. And when there's a lot of repulsive forces between the group, the surface area of contact will be lesser. And when there's a lesser surface area of contact, your London dispersion forces will be weaker. Are you all clear? Over on the other side, over here, because the two bulky groups are on opposite sides, yes? Therefore, because they are on opposite sides, when we try to pack them, they will pack a lot better because the hydrogen atom that you see here has only one electron. So the amount of repulsion that they're going to feel with respect to one another will be a lot lesser. So therefore, surface area of contact is greater, hence London dispersion forces also greater. So in terms of melting point, trans bit cis. Are you all clear? Alright, so and that is what is written here. Are you able to see that or not? Ken? Are there any questions here, guys? No? All good, yeah?
Wait, what do they mean distortion from the electron cloud?
Means how many London dispersion forces can I form? And that's affected by the size of the that is affected by the surface area of contact. Okay, now we move on to the next one, shall we? Which is called boiling point. Okay, for boiling point, you go from what state, guys? Liquid to gas. So we cannot talk about packing efficiency anymore, yeah? Because liquids, the particles are sliding past each other. So talking about packing efficiency, surface area of contact, just not gonna cut it anymore. Does that make sense? So we talk about something else. We talk about polarity now. Are you all clear? So I would like you guys to take a look at the cis isomer. The cis isomer is polar, guys. Are you able to see that? And because it is polar, it is held together by London dispersion forces and dipole-dipole. Now, the summation of London dispersion forces and dipole-dipole is known as van der Waals forces. Clear? Over on the right-hand side, the molecule is non-polar, so only have London dispersion forces. Are you guys able to see that I cancelled the word London dispersion forces? And why did I cancel it out? Because they are the same. Because they are isomers, so their size of electron cloud is going to be the same. Therefore, I cancel. And I cannot even talk about surface area of contact because they are liquids. Liquids to gas. When you are liquid to gas, you don't talk about surface area of contact because your particles are further away from each other. You all understand? No? And that's why the London dispersion forces is a controlled variable. So are you able to see, guys? This particular cis isomer only has dipole-dipole. And because he has dipole-dipole, therefore, his boiling point outweighs the trans isomer.
PD is what?
Dipole-dipole. Permanent dipole hyphen permanent dipole.
first time results was yesterday. Who's Michael?
I have no idea, man.
May I carry on? Alright, let's carry on to the next one, guys. Okay, so for exercise number 5, in general, guys, the cis isomer, alright, the cis isomer tends to be greater than the trans isomer in terms of boiling point. Agree or not? Based on the examples on page number 28. Yes? Are you all in agreement?
Yes.
Yeah? Okay. However, if you take a look at exercise number 5, you do realize that they rotate the other direction. They said that trans-butene-dioic acid has a higher boiling point than cis-butene-dioic acid. To acknowledge to you that this is an anomaly. If it's an exam paper and if it follows the trend, they will never write down this statement. Correct or not? Because you are expected to know as an IB student that cis beats trans. Clear? In terms of boiling point. But this time round they wrote here trans-butene-dioic acid has a higher boiling point than cis-butene-dioic acid, which tells us, okay, which basically tells us that this is an anomaly. So they're asking you, which of the following statements account for the difference in the boiling point between this pair of isomers? Now, this one also uses what we learned in chem bonding. I would like you guys to take a look at the two functional groups called carboxylic acid. Can you see that? The two functional groups in cis are in close proximity to each other, while in trans they are very, very far apart from each other. Can you see the two COH group are on opposite sides? When you have two functional groups that are very, very close to each other, guys, they form what we call as intramolecular hydrogen bonding. Are you able to see that I drew the two Lewis structures of COOH? I would strongly suggest for you guys to copy it down so that you can show the examiner that you know what is intramolecular hydrogen bonding. Come draw it out first because it's not inside the answer key. Huh?
Every week. Every single week, man.
And it's always around the same timing.
Wonder why is it always the same time? Always Google's the same time.
Okay, so guys, when you form intramolecular hydrogen bonding, correct? When you form intramolecular hydrogen bonding, what happens is that there's less extensive intermolecular hydrogen bonding. And if you recall when I taught you all chem bonding, right, at the start of the year, forming intramolecular hydrogen bonding is like forming a clique. CLIQUE. Okay? Once you are in a clique, you stop interacting with people outside the clique. And that is seen to be intermolecular. Do you understand? So, which means that when you form intramolecular hydrogen bonds, your interaction with other molecules outside the actual molecule itself will be less extensive. And how does it affect you? It affects you because the solubility will drop. Why will solubility drop? Because water is seen to be an outside molecule. It's not within the clique. So you interact lesser with water. If you interact lesser with water via hydrogen bonding, therefore your solubility will drop because you couldn't dissolve in him. That's one. Your boiling point will also drop as well. Why? Because you don't interact with another molecule of the same kind. So as a result, you will just exist as two independent molecules that don't interact with each other at all. Hence, you have less extensive intermolecular hydrogen bonding. Are you guys clear on this? Okay. However, guys, when you have when your two functional groups are very, very far apart from each other, like this, you can see in trans, they are very, very far apart. The two COH groups are very far apart. What's the significance, guys, when the two COH groups are very far apart? That basically tells us that no don't say no hydrogen bond, no intramolecular hydrogen bond is going to be formed. And when you don't have this intramolecular hydrogen bond, you'll be more open to form extensive intermolecular hydrogen bonding. And as a result of that, your boiling point will increase. Are you now able to see how even though you have same molecular, you have the same structure, yet your physical properties are different? So let's go through the answers here. Question number 1. The forces holding cis-butene diuic acid molecules together are weaker and is as a result of less extensive intermolecular hydrogen bonding. Okay, this is true. Number 2. Intramolecular hydrogen bonding is present only in cis-butene diuic acid. This is true as well, right? Why? Because in trans, the two COH groups are too far apart. More extensive intermolecular hydrogen bonding is present in trans-butene diuic acid. This is true as well because when they don't form intra, they tend to form inter. Are you all clear on this? Okay. And you're done. Now could you all turn over to page number 2 and identify compounds that has cis-trans isomers.
So you said the EZ isomerism is that a type of cis-trans?
Yeah. Cis-trans is said to be a subset
Also
of EZ.
So like
They only meet one criteria. They don't have to have similar groups across carbon-carbon double bond. Alright, so let's start off with the first one. The first one is a form of cis-trans isomerism. Okay, so as you can see, this is trans, right? Opposite side. This one is cis, similar side. Number two, okay, I cannot call it cis-trans isomer because they don't even have what, guys?
Like similar.
Sorry again. They don't have similar groups across the carbon-carbon double bond. This one is EZ isomer. This is not cis-trans. If you all and you do realize, guys, even though he is EZ, both are E. Are you able to see that?
Yes.
Yes, huh? Okay. How about number 3, guys? Why number 3 is wrong? Why is number 3 wrong?
The groups are different.
No, you went too far. No need to go very, very far. For you to be isomers, you need to have the same what formula?
Oh, same.
Molecular formula. You realize that number 3, the molecular formula is not even the same.
Yeah.
Am I right, guys?
Yeah.
Yeah. So therefore, number 3 is out. So hence number 1
How do
only.
you read the first one?
Which one?
Like the first
Because
one.
wedge means coming towards you,
Uh-huh.
dash means going away from you.
So the
so-
carbon bond is where?
Huh?
Where's the carbon bond?
The carbon double bond is here. Lor.
Oh.
You treat this like a double bond.
I thought you mentioned that cis-trans doesn't exist for C6 and above.
Yeah, but this one, they're just giving you an example. They still have, but a smaller degree.
Are you watching the match?
How much? Right. Of course.
Who's the one with
I also want to see high scoring.
Okay, let's carry on to the next one. Can I? Okay, hang on.
the
Enantiomerism.
Christian house, bro. You're gonna be in a imposter in the house. You're an imposter in the house.
Huh? Oh, awesome.
Cat food. Fucking expensive.
Hey, hey, why does a cat? Why do the cats never come out? Bro? They're always hiding.
He's damn scared.
Oh, really?
Yeah. He's scared of humans. Like sometimes he's scared of me also.
What the heck?
You get a cat for what? If you're
gonna
there.
pet him, like you gotta go slow.
Which breed is it? Huh?
Really short.
Oh, same ah.
Yeah. Because like he used to have depression also. Yeah. Because like
How do you diagnose whether a cat got depression?
because he went back to London. What? With the owner. And then he got depression in London.
Oh,
Then he came
what do
back.
you mean he got
Like he
depression?
kept like changing environments. Then he got
What the
sad
hell?
or some shit.
You're trauma, then you don't just see human anymore.
Aye.
Why do you buy this damaged cat?
What the fuck? Because the owner didn't want it anymore.
Oh, free?
Yeah, they don't.
Hey, give me money. That's a sick name.
Merlin.
Yeah, sick name, bro.
What is catchy?
It's not a nice name.
Merlin.
It's not a nice name.
Okay.
What I old one was the other name, Color C.
Bro, she's damn cute, bro.
Yeah. But she also never come out last time.
No, but she likes people.
Yeah, but then when she got old, then she
No,
stopped
because
like
like she was like very sick.
She got old.
And then she just leaves.
Yeah, yeah.
Okay.
Wait, how old is Sky? Like 3 years old. 3 years old.
5.
You were
Cool
you
people.
What? What's
Oh,
wrong?
okay.
so like Ollie is still not back.
Yeah.
He's not
It's okay, what? Got recording, man.
Feeling inside, bro.
Okay, so we move on to enantiomerism, okay, guys? Can? It's like an hour for each isomer, if you realize. Cis-trans will be an hour, this one is another hour. This one is a lot more complicated.
What's this?
Alright, okay, so the story of enantiomers actually arises because of death. Alright, people actually died while taking medication. Alright, this is a true story that happened in 1952. Actually, the story is actually bracketed or boxed up here on page number 34. So I'm just gonna summarize for you what exactly happened so that you know what exactly y'all are studying lah, and what's the the significance of studying this. All right. Now you see, guys, the nature, right, always selects the correct isomer that allows us to have a fine cure for our sickness. You all understand? Nature selects the correct one. So what exactly happens is, this thalidomide is a medication that is used to cure morning sickness in pregnant women. Okay, and it's actually extracted from plants. All right. But with world population increasing during the 1950s, I'm pretty sure you all heard of a baby boom or population boom during that period of time. This medication, the rate in which they were extracting this medication from plants is beyond the, what do you call it, the threshold. So as a result, scientists started creating their own form of thalidomide. And where did they get that idea to create their own is because just 10 years before 1952, it was World War II, and they were happily creating this medication called penicillin. Have you heard of this medication before?
Mm-hmm.
Yeah, and they were using it on patients to cure their war wounds and all that, because penicillin kills bacteria. All right. So what exactly happened is they used the same template to make penicillin as well. What they didn't realize is when they started administering to pregnant ladies, right, the effects didn't appear at all on the pregnant lady at first. So think about it, there's the natural thalidomide, which it comes from plants, and the synthesized one that comes from the lab, okay, which is the picture on the right hand side. Now, when you are in 1952, you don't have this, all right, you don't have these two pictures at all. You just think that what you were synthesizing is the same one as the one from the plants. Are you all clear? So they started administering it to pregnant ladies, and the effects were not apparent at the start. It only was apparent when the pregnant lady starts to give birth, and they realized that when they started giving birth, there were deformities in the fetuses. So some born with no limb, some born with half a limb, and all that. And so they realized that they were wondering, where did the source come from? So they realized that there was something in common across all these pregnant ladies, and that they were taking the synthesized thalidomide, the one that is created in the lab. So they went to study, all right? They went to study the two structures, and they still couldn't find a reason why they still couldn't find a reason, guys, why the pregnant ladies had deformities in their children that they were giving birth to. Okay, so what happens is that they were looking at the structure, and they look almost identical to each other. Are you able to see it? They are like mirror images of each other. Can you see that? So scientists at that point of time couldn't figure out what exactly happened until they created this machine called a polarimeter. All right. So if I were to indulge you guys back to the front page, this particular machine here. If you still recall, guys, polarimeter was actually taught to you guys in the chapter of chem bonding to determine the polarity of an organic molecule, whether a molecule is polar or non-polar. Correct or not? So they use this same machine, guys, all right, because you see, when you are given these two molecules like this, right, when you're given these two molecules like this, all right, when you're given these two molecules, you test for everything. You test for melting point, you test for boiling point, you test for density. All the results came the same. So they test for everything, including their polarity. So what they did was they put these two, they put these two medication, these two thalidomide, the natural thalidomide on the left, and the synthesized thalidomide into the polarimeter, which is this machine here. Now this machine here, how it works is very simple, yeah. As you all know, light travels in all wavelength. So we choose one wavelength. So from 400 to 700, we choose a wavelength. IUPAC has chosen the wavelength called 450. IUPAC is an organization that standardizes everything in chemistry so that we speak the same lingo. You understand? 450 nanometers. So out of the 301 wavelengths, we choose one wavelength. When we make a choice of one wavelength, we call it polarized light. Understand? Clear? Polarized light. So now light travels in one wavelength. all right, passing through this pinhole. So if you think about pinhole camera, it works the same way. So after that happens, right, light travels in waves and hit this canister here, and this cylindrical rod has a canister on top. So we can open the canister and insert or use a micro syringe to pump in the two thalidomide molecules. So what they did, guys, was this. Okay, the cylindrical rod is a very, very simple rod that they created back in the 1950s. So at the front is where you put your eye through so that you'll be able to see. At the end, here there's a protractor. Okay, there's a protractor because by right, the machine is used to test for polarity, right? So if you want to study individual dipole moments, you need a protractor here. So when I look through this particular machine, right, okay, I'll be able to see Ethan's face, correct or not? Agree not? I'll be able to see Ethan's face. But now I open the canister and I put in thalidomide, the natural thalidomide inside, and I look through, suddenly Ethan's face is gone. Okay? So what exactly happens is this, guys. What they realized was, what they realized was, when I started rotating the polarimeter, the angle on the protractor starts reading off how much you have rotated by. So let's say I have rotated 10 degrees anti-clockwise, I'll be able to see Ethan's face again. Clear? So at the start, I couldn't see Ethan's face. I rotate and rotate and rotate and rotate until I'm able to see Ethan's face, and I realize that it has rotated 10 degrees anti-clockwise. Clear?
Oh, yes.
Okay? Then I put in the synthesized thalidomide into the same machine. Of course, I removed the natural one, and I put in again, and I didn't see Ethan's face. So I started rotating 10 degrees anti-clockwise as well, hoping to see Ethan's face again. But then they realized that when I rotated 10 degrees anti-clockwise, I still couldn't see Ethan's face. So what I did was I rotated at clockwise direction. And when I rotated 10 degrees clockwise, I could see Ethan's face again. So then they realized that the two molecules of thalidomide, one natural, one synthesized, actually rotated to the same angle but to differing directions. The natural one was rotating anti-clockwise, but the synthesized one was rotating in clockwise direction, but by the same magnitude, which is 10 degrees, for example. I'm just giving you a number by 10 degrees. So as a result, these two molecules are rendered to be different. You all understand? No? They're not the same molecule that we thought it was, that the scientists thought it was, that they thought that they were synthesizing from nature. So as a result, when they synthesized the other molecule, the synthesized thalidomide, they were actually synthesizing the wrong molecule. And this wrong molecule has caused about 17 deaths, all right, because it was fed to the pregnant woman to cure morning sickness. And when some fetuses were born, some of them were born stillborn. All right, stillborn means when they give birth, no heartbeat. No. Clear? All right. So what is the take home message here? The take home message here is that when this particular phenomena in 1952 raised awareness of the need for us to study molecules in depth, especially if you are synthesizing it yourself or in the lab. You all understand? No? Clear? Most of the times, guys, you might be thinking, then how did they synthesize penicillin without having this problem during the World War? Because for penicillin, when they synthesize penicillin, the natural version, which is the fake version, right, will give the same effect and will not give any what we call as teratogenic effect, which means negative effect on the body. There are some isomers, right, guys, that when you give it to the patient, you just don't feel any effect. No? You don't get better, neither do you get any worse. So people will be able to tell that you have synthesized the wrong molecule. There are some isomers that when you synthesize naturally, has the same effect as the actual natural isomer, even though the two molecules are different. But it is only because in thalidomide, right, that it causes death, and that's why people started investigating. And then they realized And then they realize, guys, that they synthesize the wrong isomer, and hence they studied in depth on what is the criteria, okay, for you to exhibit this type of isomerism. And this type of isomerism is known as enantiomerism. Clear? So just now I keep on using the term natural thalidomide and synthesized thalidomide. In chemistry, when we call molecules like this, isomer 1 and isomer 2, we call these two isomers as enantiomers. Enantiomers, listen, enantiomers, right, are basically non-superimposable mirror images of each other. So I'm going to break down the words for you guys. What exactly is non-superimposable and what exactly is mirror image? I'm pretty sure you all understand what is mirror image. So non-superimposable means the object and the image are not be able to superimpose on one another. Like how? Like your pair of hands. For example, you cannot superimpose your right hand onto your left hand because your pinky will match with your thumb. Can you see that? So these pair of hands are said to be enantiomers of each other. They are mirror images of each other, but they are non-superimposable. Are you all clear? So are there such thing as superimposable mirror images of each other then? The answer is no. The answer is yes, superimposable mirror images, like for example his glasses. Alright? Okay. This particular cup. Alright? This particular cup, if you notice over here, correct? Agree not? This particular cup, because it has an internal plane of symmetry. The two of them, your glasses as well, they have an internal plane of symmetry. A pair of socks, for example, has an internal plane of symmetry as well. That's why it doesn't matter whether you wear the left or right, because there's no direction when you are wearing a pair of socks, unless obviously you wear the pair of socks that has the toes in it, you know, the socks that has toes. That one matters. But what I'm trying to say is that non-superimposable mirror images are basically what we call as enantiomers. Are you all clear, guys? So for you to be enantiomeric, you need to meet the prerequisite to be enantiomeric. And the prerequisites are on the next page over here. Okay?
Are there any cases of like the one version of the drug is like more potent than the other, but both work?
Yes, have. That one is cisplatin. Why?
Curious George.
Wow.
Potence.
Curious fee. Inventor fee. Super fee curious.
Are there any cases of enantiomers for non-organic molecules?
Yes, of course. Okay, so let's start off with the very first one, guys. Okay. The first thing is we need to have a chiral carbon. Okay. Come turn to the next page. What exactly is a chiral carbon? A chiral carbon is an sp3 carbon bonded to 4 differing groups. Okay? So a chiral carbon is an sp3 hybridized carbon bonded to 4 differing groups. Now you might be thinking, why is this a criteria? Okay, look, when you were happily putting the molecule, alright, into a canister just now, why did I have to rotate the polarimeter in order to see Ethan's face again? The reason is because when you have 4 differing groups, that means you have 4 electron clouds. When you have 4 electron clouds, the manner in which light interacts with these 4 electron clouds are different. So that means that light cannot pass through the molecule itself. So what light does is, light goes around. By rotating the polarimeter until I saw Ethan's face, I bypassed the molecule. Get it? And we say that the molecule have rotated the plane of polarized light. Because, why do we say that he has rotated the plane of polarized light? Because light cannot pass through him. So therefore light has to be rotated in order to get past. And when you are able to do that, we say that you're optically active. Understand or not? Obviously, you don't have to explain all this in exam, yeah? You just need to be able to explain what's a chiral carbon. A chiral carbon is basically an sp3 carbon bonded to how many groups, guys? 4 differing groups. Are you all following now? So guys, just to take a look at thalidomide, this is your chiral carbon, just in case you all are wondering. This is sp2, this is sp2, the whole molecule here is sp2. This is nitrogen. You don't study chiral nitrogens at IB level. This is the only thing that is a chiral center. Are you all clear? And there's only one chiral center, if you all notice. This is not a chiral center because it has 2 similar groups. The same thing can be said over here. Are you all clear now? So if one is rotating clockwise, the other fella is rotating anti-clockwise, but by the same magnitude. Hey, are you all clear now?
Yeah.
Okay. You all understand, right? Okay, so let's go through the second criteria. The second criteria is there is no plane of symmetry. So the molecule cannot have an internal plane of symmetry. Because when the molecule has an internal plane of symmetry, the 2 enantiomers that you thought were enantiomeric are actually the same molecule. I will show you a video or else you all will not know what the hell I'm talking about. This is an example of a molecule that has an internal plane. Can you take a look? It has a chiral carbon. Are you able to see that? It has a chiral carbon. But it has an internal plane of symmetry. Can you see, you know? When a molecule has an internal plane of symmetry, one of the isomers are going to be identical to the other. And I'm going to show you a video about it. We call these molecules that has an internal plane of symmetry as meso compounds. Just in case you want to know where the name is, it's right here, MESO. A stereoisomer that has chiral centers but is optically inactive due to a internal plane of symmetry.
What does optically inactive mean?
Means it doesn't rotate the plane of polarized light, no? When I put the molecule inside the canister just now, I can see Ethan's face. It didn't turn pitch black. That's the meaning of optically inactive. It does not rotate the plane of polarized light. And the third one, which you're going to cover in the subsequent chapters over the month of June, right? Actually, tomorrow you all will start covering already, because you all are the first class to embark on the next one. Huh? Correct, right? It's called a racemic mixture, guys. Are you able to see that? So what is a racemic mixture? A racemic mixture happens when you have 50% of each enantiomer. Are you all able to see this picture here? This picture here are mirror images of each other, right? But they are not superimposable. Which means that if I take the image and I put it on top of the object, I will not be able to superimpose them. So we call this enantiomer. If you have 50% of each enantiomer, let's say this one rotates 10 degrees anti-clockwise, this one rotates 10 degrees clockwise, you will have no net rotation. Can you see it becomes 0 degrees?
Yeah. So isn't it all 50%?
No, sometimes you create 80-20. Yeah.
Oh,
It's not always 50-50, guys. Actually, to have 50-50 is quite rare. This phenomena is very, very rare for you to get this 50-50 of each enantiomer. 50-50 of each enantiomer is called a racemic mixture. Is that clear, guys? Alright, so before I carry on further, yeah. Hey, hello, come. The terms chiral is sp3 carbon bonded to 4 differing groups. Optical activity is defined as the ability to rotate the plane of polarized light. Enantiomer is non-superimposable mirror images of each other. And lastly, racemic mixture is defined as 50-50 of each enantiomer. Are you all clear? Do you all understand all these terms?
yes.
Yes, huh? Okay.
Wait, you explain one, could you explain again? Like using the diagram.
Huh?
Like using the diagram. Can you explain this one?
What is it?
Using that, so you have 50% of each of these enantiomer. So when you have 50% of each, because the molecule on the right rotates clockwise, molecule on the left rotates anti-clockwise. So when I calculate, I'll get 0 degrees. So what I'm trying to tell you here is this, guys. Doesn't mean you have a chiral center automatically warrants you to be optically active. Understand? You need to be in line with the other two criteria. The other two criteria is you cannot have an internal plane of symmetry and you cannot be in a racemic mixture. So let us repeat ourselves. For you to be optically active, you need to have a chiral carbon. What's a chiral carbon? sp3 carbon bonded to 4 differing groups. You cannot have an internal plane of symmetry. And lastly, guys, what's the last one?
Non-super.
Nope. The last one is you cannot be in a racemic mixture. Okay, that's the third one.
But doesn't that mean not very isn't it the same as not having a plane of symmetry?
Nope. Not having a plane of symmetry is your mirror images are non-superimposable.
Oh.
Because if you have an internal plane of symmetry, that means your mirror images are superimposable. What? Yes, Ethan.
So racemic, it just means like same amount of each.
Same amount of each enantiomer.
So if it's non-racemic.
Non-racemic, that means
so
that
it's like different.
varying amounts of each, and therefore you will have a net rotation, and therefore you're optically active.
Also, like if it's equal, you can't.
You can see you'll be optically inactive.
So then how would they know if, like, then how would they know that they are different?
How do they know they are what?
Like if it's not optically active, right? Then like you can't use the tube thing.
But they already know that because they will have a pure sample of the anti-clockwise one and they will have a pure sample of the clockwise version of the enantiomer, right? So now when they put equal amounts inside, they realize that it's 0 degrees. And therefore they will know that, because it's 50-50, that's why it's 0 degrees.
Oh.
Yeah, we call it enantiomeric excess. EE.
Oh, so they just don't put the same amount.
Yeah,
So then after you can see.
correct.
Okay.
Or the other way will be you already know what you're synthesizing, right? So you will know there is a chiral carbon, for example. Then when you put when you test for sample, right, you realize that how come it's optically inactive? Then you suspect there's 50% each of each of the enantiomer. That's why it's optically inactive. Okay? May I carry on to the next part? So, are y'all okay now? You need to be able to draw this here, guys. This particular picture, you need to be able to draw. How do you label chiral centers? You need to label them like this. Can you see that? Alright, you have to label them in this manner. And then the distance from object to image, object to mirror must be the same as mirror to image. Make sense? Whether you put W here doesn't matter. Which substituent doesn't matter. You all know why? You know why it doesn't matter where you put W, X, Y, and Z? Because sigma bonds are constantly rotating. I mentioned this at the start of lesson. When light passes through molecules, they are always rotating. So where you put your W, your X, your Y, your Z doesn't matter. But what matters is the distance from Z to the mirror must be the same as mirror to the image. Isn't this what you all were taught in physics as well, if you take physics in secondary school? Right? Correct now? So it really doesn't matter where you put W, X, Y, and Z. What matters is the distance from the mirror to the mirror and the mirror to the image. Are you all clear? So why am I highlighting this, guys? I'm highlighting this because of wedge dash type representations involving tapered bonds should be used for the representation of enantiomers. Okay? Clear? Then, describe and explain a chiral carbon atom giving rise to stereoisomers with differing optical properties. So you need to be able to describe what a chiral carbon is. It is an sp3 carbon bonded to 4 differing groups. Explain why chiral carbon give rise to stereoisomers, because they have four different groups that interacts with light differently, right? And therefore it creates differing optical properties. Clear? And lastly, guys, you need to recognize a pair of enantiomers as non-superimposable mirror images. Okay, what do they mean by that? This last point, which means I give you a molecule like this. Could you identify to me where is the chiral center? The blue dot, exactly. Of course, molecules can get more complicated than this lah, but we shall not go there for now, okay? Now, we're still not done yet. Alright? Ready to carry on to the next part? Diastereomers, guys.
Bro, we're still on top of it. It's actually really. Yeah, so no, actually, I thought it was also by
Okay, ready? Alright. Now, this, you will only see diastereomers, yeah? Okay, you only see diastereomers and meso compound, which is on the following, what page is it? 33, right?
Yes.
On page number 33. When you have 2 chiral centers or more, okay? You will not see meso or diastereomer when you only have 1 chiral center. Alright, so let's take a look at this, shall we? Now, I drew out this molecule in green. As you probably could tell, there are 2 chiral centers. Are you able to see that? Now, let's think about the possibilities when it's 2 chiral centers. You could be clockwise, 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 anti-clockwise, anti-clockwise, clockwise, and the last one is anti-anti, correct or not? So that is 4 possible combinations. And how I got that is, I take the number 2, and raise it to the number of chiral centers. So there will be 4 stereoisomers in theory. In theory, this is the max number that you can form. Why is it max number? Because we haven't taken into consideration that there could be an internal plane of symmetry. And when there's an internal plane of symmetry, instead of 4 stereoisomers, it become 3 stereoisomers. Because 2 of the molecules will look identical to each other. So what I did today, what I did for the other classes, was I drew out for them the 4 possible combinations. Clear on this? And I drew them in differing colors. Can you see that? So if you start off with the purple one, guys, if you start off with the purple color, you do realize that really not. I labeled it as A, C, B, and D. Hey, listen up. Listen, very important. So, this is wedge. This is dash. Correct? Wedge means coming towards you. Dash means going away from you. So your enantiomeric pair, okay, will be dash and wedge. So purple and green are enantiomers of each other. For those of you who want it to be more technical, if this is rotating clockwise, this is rotating anti-clockwise. If this is rotating anti-clockwise, this is rotating clockwise. Make sense? Always remember, when you are enantiomer of each other, you must, the number, let's say you have 5 chiral centers. All 5 chiral centers must be different from its enantiomer. So let's say I have 3 chiral centers. I am clockwise, clockwise, clockwise. He, who is my enantiomer, will be anti-clockwise, anti-clockwise, anti-clockwise. Make sense? So right now, if this is clockwise, anti-clockwise, his enantiomer must be anti-clockwise and clockwise. Are you all following so far? Alright? Must remember that. that is what we call as enantiomers. Enantiomers means they differ at every single chiral center. Now B and D, are you guys able to see that they are enantiomers as well? Wedge, wedge, dash, dash. So if this is clockwise, clockwise, guess what is this? Anti-clockwise, anti-clockwise. Are you all following?
Yes.
Yes, crystal clear. Okay, so I repeat myself again. Enantiomers differ from each other at every single chiral center. Okay, now the question is, what's the relationship between A and B? A and B, they share at one chiral center, but they differ at multiple at the other chiral center. Now A and B rather, we call them diastereomers. For you to be diastereomers, you need to share at one chiral center, and the other chiral center doesn't matter whether you share or you don't share. You understand now? The key ingredient here for you to be diastereomers is you need to share at one chiral center. Share means what? Share the same rotation pattern at one chiral center. And the other chiral centers, it could be different or the same, it doesn't matter. Does that make sense, guys?
Yeah.
For you to, okay, let's repeat that. For you to be enantiomer, you need to be different at every single chiral center. But for you to be diastereomers, you need to be same at just one. Once you are same at one, right, that means that you are confirmed cannot be enantiomer already. You are a diastereomer of this molecule.
Only one.
Only one. You just have to be the same at one.
Okay.
Okay? Understood?
Also the top and the bottom.
The top and the bottom are diastereomers. The top and across are diastereomers as well.
Okay.
Okay, got it? You all understand not?
Yes.
How we identify. But I'm taking it with a pinch of salt because they didn't write it in the chem guide, but it was tested in the old syllabus. So I'm just teaching you just in case. So what they will do, in 2020, guys, they drew these 4 molecules for the students, and they labeled this as well, A, B, C, D, guys. They labeled for the student A, B, C, D, and then they ask you, could you name me the enantiomeric pair? Could you name me the diastereomic pair? Get it? That's what they did for. That's what they asked the student to do. They will draw the 4 molecules for you, and then they ask you which one is diastereomer, which one is enantiomer. Okay, as an MCQ.
So what's the main difference between both?
Sorry again.
The main difference.
Enantiomer differ at all chiral center. Diastereomers same at one chiral center but differ at every other chiral center that you have. So the key ingredient for diastereomer is to find their common relationship between the two of them. Once you're able to see that they have the same rotation pattern, you know that they're diastereomer already. Clear?
Yes.
Okay, we're not done yet. Now I want to go into the next part, which is called meso compound, but I cannot go into that until I show you a video. All right, for meso compound, yeah.
And we have our bromine going up and our hydrogen going down.
Bro.
Okay, so guys, this is what I have just did just now. All right, if you realize, let's do a recap. If you all understood what I taught, could you all tell me which one are supposed to be enantiomeric pairs?
Yes.
1 and 2 and 3 and 4.
Very good. 1 and 2, as well as 3 and 4 are enantiomeric pairs. Can see that? So your diastereomers are 1 and 3, and 1 and 4, correct? And 2 and 3, and 2 and 4. Make sense? Those are your diastereomic pairs, which means they share at one chiral center, differ at the other. Clear? Right now, guys, we want to know, right, whether there's an internal plane of symmetry. Which means what? He said just now that 3 and 4 is an enantiomeric pair. But these two molecules could be the same thing. So if they are the same thing, when we are drawing them, this and this are equivalent to each other. So 3 and 4 is the same as just 3. So we need to take a look at your at your molymod or your organic molecule to see whether or not the molecule has an internal plane of symmetry. So that therefore it won't be 4 stereoisomers, it will only be 3 because the 2 molecules that we have just drawn are exactly the same molecule. Does that make sense, guys? So let's take a look at this.
I'll put a question mark here again.
Oops, sorry. Okay.
3 and 4. And let's examine the relationship between 1 and 2 first. On the left is stereoisomer 1, and I've left the hydrogens off the methyl groups and the OH just so we can see the models better. So here's our carbon chain, and we have both OHs coming out at us in space. And then for stereoisomer 2, here's the carbon chain, and we have both OHs going away from us. So I'm going to hold them in the way they are in the drawing, and I'm going to rotate the one on the right. And when I do that, we can see that these are mirror images of each other.
Can see?
If I try to superimpose one on the other, so I'll just rotate this one back here and flip it over, you can see they don't match up. So the atoms don't line up here. So they're non-superimposable. Doesn't matter how you do it, I'll rotate it again, and we can see we can't superimpose our atoms. So these are non-superimposable mirror images of each other. These are enantiomers. And we can check for a plane of symmetry, so I can take one.
So now they're checking plane of symmetry as well.
So we have our hydrogens going away from us in space. And I look for a plane of symmetry, but I don't see one. So this is not a meso compound. So 1 and 2 are enantiomers.
So we confirm, he did 3 checks if you realize. What are the 3 checks that he did? Number 1, he checked whether they are mirror images. Okay. Number 2, he checked whether or not they are not superimposable on each other. Correct or not? Number 3, he went to check internal plane of symmetry. And he realized that they are non-superimposable mirror images and they don't have an internal plane of symmetry. Understand? Now what he's going to do is he's going to compare 3 and 4. Okay?
Images of each other. And we could have guessed that because if we look at our chiral centers here, so this one has an OH coming out at us, and then that one has it going away from us. This one has an OH coming out at us, and this one has it going away from us. We have opposite configurations at both chirality centers. Let's look at 3 and 4 next. So what is the relationship between these two? Well, at first, we might think these could be enantiomers, because at this carbon we have OH on a wedge, and then here we have OH on a dash. And then here we have OH on a dash, and here we have it on a wedge. So that might be your first guess. But let's look at the video, and let's look at the model sets to help us out. Remember, I'm leaving the hydrogens off the methyl groups and the hydrogens off the oxygens in the video just to help us see the molecule more clearly. On the left, we have a model of drawing 3. So here's our carbon chain with an OH going away from us in space and an OH coming out at us in space. On the right is a model of drawing 4. Here's our carbon chain with an OH coming out at us in space and an OH going away from us in space. So I'll hold the 2 models and we'll compare them. First, let's see if they are mirror images of each other. So I'll take the one on the right and I'll rotate it and I'll hold it up next to the one on the left. And now we can see that these 2 are mirror images of each other. So next, let's see if one is superimposable on the other. So I'll go back to the starting point and I'll rotate it around like that. And let's see if we can superimpose the one on the right, the mirror image, on the molecule on the left. Notice that we can. All of the atoms line up. So all of the hydrogens, carbons, and oxygens are in the same place. So this is a compound that has chirality centers, but it is achiral. The mirror image is superimposable on itself. So we should be able to find a plane of symmetry. So I'll just pick one of these models, it doesn't matter which one, because they represent the same compound, and I'll rotate around so we can see a plane of symmetry. So right there is our plane of symmetry. This is a meso compound. So 3 and 4 actually represent the same compounds.
Can you see that? 3 and 4 is the same compound. So they are what we call as meso compounds. So by right, you're supposed to have 4 stereoisomers, right? Because it's 2 to the power of 2 chiral centers, correct or not? But actually when they put the 2 molecules together, you do realize that there's an internal plane of symmetry. And when there is an internal plane of symmetry, guys, the 2 molecules are actually the same molecule that we have just drawn. So instead of 4 stereoisomers, we now have how many stereoisomers? 3
Wait, so
stereoisomers
we
of
have
each
to know
other.
how to recognize it. Just
Of
from
course.
Just from that.
Yes, you need to know how to recognize it.
So these are enantiomers.
Sorry, yes, 3 and 4 are not enantiomers. They are actually superimposable mirror images of each other. And this is what we call as meso compound. Understand, guys? Are y'all crystal clear on this? Can, huh? But again, as having said that, not written in Chem Guide, but I just teach you just in case it comes out. Okay? Can, huh? Alright, going back to our structure. So that's why, guys, what I wrote here is actually A equals to C, right, guys? Correct or not? Oops. It's supposed to be A is equals to C, but because they have an internal plane of symmetry, we cancel the A, and then we just say that C, B, and D are the stereoisomers of this particular molecule.
Because A is just C.
A is just C, exactly. Very good, yeah. Clear or not?
Let me check.
Can, huh? You all understand not what's going on? Yeah? I'm this is not an easy chapter, as you probably could tell. That's why we need to practice, which is tomorrow's lesson basically for you guys. We need to practice finding chiral centers, and we need to draw molecules with regards to this. Can? Alright, we're still not done yet. There's still just one last part. Okay? Take a look at your enantiomers, guys. Now, for physical properties of enantiomers, everything is the same. You can see, density is the same, refractive index is the same, color is the same, melting boiling point is the same. The only thing that they differ in their physical properties is their effects on plane of polarized light and their interaction with other enantiomers. So if I'm anti-clockwise, I want to interact with another enantiomer. My interaction is different from when a clockwise interacts with that same molecule. Clear?
Mm-hmm.
Let's say, for example, if you all still cannot picture it, Oliver and KN are enantiomers. Ethan is another enantiomer, but it's not related to the two of you. How Oliver interacts with Ethan is different from how KN interacts with Ethan. And that's how we separate the two enantiomers apart from one another. How they react, you all as an IB student don't need to know, but you just need to know this, guys. Hey, listen. Knowledge of the different chemical properties of enantiomers can be limited to the fact that they behave differently in chiral environments, which is whatever that I say. How he interact, even though they are enantiomers, how he interacts with another chiral molecule is different from his enantiomeric pair. Are you all clear? And that's all that you need to know. This part is usually tested in MCQ. They will ask you about which of the following are properties of enantiomers. Everything same. They rotate plane of polarized light to different directions but same magnitude, and they interact in chemical property sense. They interact with molecules differently. Alright, particularly molecules that contain chiral centers. Clear? Alright, the last part of today's lesson, okay, will be exercise number 6. Okay, I drew out the molecule. I converted the condensed formula. You might want to copy this first. I do a conversion for you guys because I scared that it will take too long. Alright, okay, you all have copied, very good. Now, let's start off with the molecule on the left part of the molecule first. Are you guys able to tell that this particular molecule here has each doubly bonded carbon atom has two different groups? You all agree, no? And across the carbon-carbon double bond, there are similar groups. Yes? So what I have just drawn is the cis portion. Yeah? And there's a chiral center here. Correct, no? So let's do a bit of math. There are two areas. So it could be cis clockwise, that's 1. Cis anti-clockwise, 2. Trans clockwise, 3. And trans anti-clockwise, 4. So you are going to have a total of 4 stereoisomers. You all understand, no, guys? Are you all following so far? Okay. So, okay, you all copy this down. 2 to the power n, where n represents the number of stereoisomers. I have 1 cis trans and 1 enantiomer. So grand total 4 stereoisomers. You might to copy this down as well. You'll understand what's going on, right? Okay, so guys, if you take a look at the 4 pictures over here, we do it slowly, okay? Alright, when you're given you might want to change Z to cis, because cis is a more more precise naming for this. Because if you're a Z isomer, you're obviously cis, right? Think about it, because one is a subset of the other. Am I right, guys?
Yes.
Okay, so we start off with cis. Now, when you draw a mirror image, like a mirror line there, right? The cis doesn't get affected, yeah? The cis remains cis. Doesn't mean cis suddenly becomes trans when you do a mirror image. So when you are given a cis trans as well as a chiral center and you draw a mirror line, just focus on the chiral center. Don't need to give a shit about the cis. The cis will remain a cis. Are you all clear? The trans will remain a trans. So, as I've mentioned earlier again, are you all able to see that the distance between the object to the mirror is the same as mirror to image?
Yes.
This ensures that if this is rotating clockwise, the other fella is rotating anti-clockwise. Now, just in case you all want to know how to know whether this is rotating clockwise or not, I'm just going to teach you just for the sake of enrichment. Okay? This is proton number 1. This is proton number 17. This is proton number 6. This is proton number 6. Correct now, guys? Yeah? Because of the fact that this is 6, but this is a double bond, correct now? A double bond has a higher priority as compared to a single bond. Yes? Yes? Okay. So as such, what I'm going to do is, I'm going to label priority in red. This is priority group number 1. This whole group here is priority group number 2. This whole groupie here is priority group number 3. So you go from 1 to 2, 2 to 3. What direction is this, guys? Clockwise direction. Okay, now you go over to the other side. Priority group number 1. This whole groupie here is priority group number 2. This whole group here, priority group number 3. So what direction is this? Anti-clockwise. Now, why didn't I bother about hydrogen? Because both of them priority group number 4. What? I don't give a shit because it's a controlled variable across both of them. So I didn't bother about hydrogen. I just focus on 1, 2, 3. This is for H3 students, yeah? Okay, H3 students do this. They identify the rotation of the of the molecule with the rotation of plane of polarized light, whether clockwise or anti-clockwise. But since you might be wondering, why am I so fixated that the object to mirror must be the same as mirror to image? It's because of this. When you do this, when you ensure that your object to mirror is the same as mirror to image, you have just ensured that if this is clockwise, this is anti-clockwise, or vice versa. You don't have to do this to go and count, to check whether or not it's going to rotate this way or that way. Yeah, you all clear now? Can? Alright. Okay, a last question for today, guys. Sorry, today a bit long, the lesson, right? Okay, could you all help me identify chiral centers for questions 2 and 3, please? I know the answer is there, but can you all work on the molecule on top? All right. Okay, so what did I do first? I cancel out all the oxygen atoms because they clearly can't be chiral, because we don't study chiral oxygens. That's the first thing that I do. Then I cancel all the sp2 carbons. All sp2 carbons I cancelled out. All the one in blue are sp2 carbons. Understand, guys? That's what I did. Then the third one that I cancel out are sp3 carbons, but they have same groups, HH. So I cancel those out. Then I'm only left with the intersection. Can you see the letter Y, guys, that is being formed? Now, why am I so fixated about the intersection points? Because the intersection points are where you find the chiral center. Now, you might be arguing with me, saying that this is carbon, this is also carbon, this is also carbon. Isn't that same group, right? But you see, this carbon is bonded to a carbon atom who has a hydrogen, one hydrogen. This carbon is bonded to a carbon atom that has how many hydrogen? Two. So these two carbon atoms are different. This carbon atom is bonded to a carbon atom with 3 hydrogens. So these are differing groups. Make sense? So therefore, this is a chiral center. Okay? Can? This is also a chiral center. So in conclusion, if you want to do it quickly, right, and they give you a ring, just look out for the intersection points and draw the letter Y. Once you see the letter Y, you know that these are the chiral centers. That's how you do it very, very quickly. Yes?
That this one has CH, then that one has CH.
This one is CH, right?
Yeah.
Then?
I'm asking why that one is CH and the other one is CH too.
This one is CH2.
Yeah.
Because carbon got 4 bonds. 2 bonds already used, so left with 2 more. Never draw, ma. CH bonds are not drawn, right? Yes? Hey, agree not? Is it too difficult, guys?
No.
In this case, would it not be considered a chiral carbon?
This one is not.
Okay.
Wait this one here and here is the same. No. This is a chiral carbon. You know why? Because this carbon is bonded to oxygen, while this carbon is bonded to a carbon atom. Yeah.
Oh, weird.
Yeah. If you want it to be symmetrical, you have to draw a hexagonal ring. Then the oxygen right at the bottom. Then it will be, then you can say that it is not chiral.
Oh, because those are double bond.
Yeah. Yeah. sp2. Okay, number 3. Are you able to get 0 chiral centers? You all haven't done this in school, right, guys?
No.
We're using the Molly mod, whatever that is.